Now let's look at a very important topic, matrix theory, which is eigenvalue, which is called eigenvalues and eigenvectors. Now let's start with the definition. Uh, let A be a C(n cross n) matrix. So one thing to note is that eigenvalues are defined for square matrices. The field of the matrix doesn't matter; it can be real or complex. And let's say we have an X, which belongs to Rn, or it can be also Cn, doesn't matter. And X is not equal to 0. Then if A into X is equal to lambda X, then lambda and X are called as an eigenvector, eigenvalue pair. So what does that mean? That means is there are some set of vectors which when multiplied with A, they don't, the linear transformation is such that they only undergo scaling. They don't change the direction, right? But this is for the real eigenvalues. We have to be, there are complex cases where this doesn't actually hold. But for the complex cases, it's anywhere rotated. There are no such eigenvalues which are real. Okay. Fine. So how do we find the eigenvalues? From this equation, which we've already seen, Ax is equal to lambda x. So Ax minus lambda x is equal to 0. From there, you can write A minus lambda x is equal to 0. As you see, whenever we have a matrix of the form, so like some D into x is equal to 0, where x not equal to 0, this means that the null space of the matrix D is not trivial. Right? And similar case, the A minus lambda x into x is equal to 0, which means that the null space of A minus lambda is not trivial, which means that A minus lambda is singular. A minus lambda is singular. So if A minus lambda is singular, determinant of that will be equal to 0. Fine. So also one way of looking at it, if we have any matrix, if we know the eigenvalues and you subtract the lambda I from that from that matrix, you can turn that matrix into a singular matrix. That is also another way of looking at it. It's actually a fascinating aspect of it. So this equation is known as the characteristic equation. Determinant of A minus lambda is known as the characteristic polynomial, and it's of degree n. So there are a few more terms which we can look at. The spectrum of a matrix A, which is denoted by sigma of A, is actually the set of all eigenvalues of A. So that's the spectrum of A, and the spectral radius, which is denoted by rho of A, is the maximum mode sigma. Note that it's not maximum sigma, it's maximum mode sigma. Sigma can be real as well as complex. Okay, so sigma belong to C here. Sorry, it's not sigma, lambda, mode lambda, where lambda belong to the spectral radius. Spectral radius we've already seen in an earlier video. And we've always known that spectral radius is a tight reservoir bond and all those things. Or often known. So there are a few more properties which were remarks which I would like to take a look. The proofs of these remarks are actually pretty straightforward. So I won't be proving this here. I'll give a sketch of the proof and you can prove it. It's very easy. Suppose A lambda x is equal to lambda x, then we know that lambda is the corresponding eigenvalue and x is the eigenvector. Then, sorry, it's x. Then if you scale x by a factor c, then a into cx is again lambda times cx, right? A into c of x is lambda times cx. Then it is cx is again an eigenvector of A with the corresponding eigenvalue lambda. Fine, this is straightforward. Now another thing is let we have a polynomial p of t, which is given by which is a kth degree polynomial. given by ak t raised to k plus ak minus 1 t raised to k minus 1 plus etc. plus a0. And if let's say we have a for which lambda is actually the eigenvalue of a and x is the corresponding eigenvector, then suppose we have p of a. So p of a is actually, it is written as p of a will be ak a raised to k. A raised to k is actually conformable with a. Like if a is actually n cross n, then a raised to k is also n cross n matrix. Plus a raised to k minus 1 k minus 1 plus etc. plus a0 into 8. So this is how we define P of A, which is another matrix. So in that case, lambda is eigenvector. Let lambda is eigenvector value of A with corresponding eigenvalue of X. And what is the eigenvector of eigenvalue of P of A? We don't have to. It's not too difficult to find the eigenvalue of P of A. It's actually P of lambda. So how we can use that? The equation you can use is a raised to k into x is actually lambda raised to k. This is the basic thing which we're using here. Using this, you can easily show that P of lambda is the eigenvalue of P of A. Okay, let's end the discussion.